All right, here we're going to learn about some special cases to factoring. So these might seem like extra things to learn, but it actually makes things a lot easier if you recognize it. If you don't recognize it, that's okay. You can always use factoring by group. So that case 2, those notes are super valuable because you can use that in any case you want. But if you recognize that A is equal to 1, or that A and C are both perfect squares, then there's just easier ways to jump to the answer without having to do that whole factoring by grouping. So that is the key to these special cases, that A and C are perfect squares. So this only works if both the coefficients of A and the constant C are perfect squares. So some of that just takes some recognition, or you can just test it. If you do the square root of A and you get a nice whole number, and you do the square root of C and you also get a whole number, that means they're perfect squares. So you can test it. Or if you just recognize it right away, like in example A, hopefully you know that 4 and 25 are both perfect squares. So sometimes it might just jump out at you, other times it might be tougher to see, but you can always test it by just doing square root of A, square root of C. See if you get a whole number. If you get a decimal, that means you cannot use this. And actually, that's what we're going to do anyway. We're going to take the square root of the first term and the square root of the last term. So I'm going to do the square root of 4x squared, which means I'm going to do the square root of the number, and I wouldn't be doing this if it's not a perfect square, so this is going to come out to a whole number. That's going to be 2. And the square root of x squared, those operations completely cancel out. Remember, we were looking for, when we were simplifying radicals, we were looking for pairs of x's that are under that square root symbol. We have one pair, and that's what it comes out as. It comes out as just 1x to the first root. So that was the square root of the first term, and we're going to do the square root of the last term. That's a little bit easier. That's just 5. So I'm going to put those together into a binomial. Basically, that is my factor. Actually, that's my only factor, because it's going to be the same thing twice. So the sign is going to be important here. So I want to think about how I'm going to add up to that middle term. So I still am using kind of the same logic. I'm thinking about what's going to add up to that b, and it's a positive b. That's the important thing. This is a positive number. So when I write this into my binomial, I'm writing this as these two numbers together, or these two expressions, terms together, 2x and 5. If this is a positive, that's a plus sign. And you can write this in two different ways. You can either write that twice. You can write this as 2x plus 5 times another 2x plus 5. Or the simpler way, 2x plus 5 squared. Anytime A and C are perfect squares and a B exists, we're going to have the same factor twice. Again, if you're not comfortable with that, if you don't recognize perfect squares easily, or you're not sure where any of those factors came from, you can use factoring by grouping and it would work just the same. I'm going to show this one more time. We're looking for the square root of the first term and last term. So the square root of 9m squared is 3m. The square root of 64 is 8. So I know that's going to make my binomial, my factor. I just have to think about how am I going to get a negative 48. If this sign is a negative in the middle, that sign is also going to be a minus. Because I want to think about, if I actually multiply these out, 3m minus 8 and another 3m minus 8, if I multiply those together, 3m times 3m is the 9m squared. Negative 8 times 3m is a negative 24m. Negative 8 times the 3m is another negative 24m. That's really where this number is coming from. That negative 48 is coming from a negative 24 and another negative 24 combining. The positive 64 is going to happen no matter what, because these signs are the same. It's a negative 8 times a negative 8, that's a positive 64. And again, the simpler way to write this, how I really want you writing this, is 3m minus 8 squared. It's showing that we have two of those same factors. The difference of squares is similar. A and C are still perfect squares, but we don't have a B. So there is no B, but really we know that actually B equals 0. It's not that there is no B. It's that the two terms canceled out. Those two like terms happened to cancel out and created a 0 for B. So there is no B term because we don't need to write it because it's 0 times x or just 0. Same exact start. We still take the square root of the first term and the square root of the second term. We don't include the sign with that number. You can't take the square root of negative 16, at least not yet. So we just take the square root of positive 16 to figure out what that number is going to be. That's going to be 4. And the square root of 9x squared is 3x. So it's similar to the previous examples where we do put those two numbers together as our terms inside the factor, inside the binomial. But if those numbers are going to cancel out, if those x terms are going to cancel out and make no b at all, then we need opposite signs. One is going to have a plus sign, and we're going to make a second one that has a minus. So it's kind of the same logic as before, where you take the square root of a, take the square root of c, and you put those two terms together. But instead of building and making a bigger x term, these are canceling out, so we need opposite signs. Really, this times that gives us a positive 12x, and this one times this one gives us a negative 12x. Those end up canceling out. When you're foiling that out, those would cancel out and make no b term at all. I'm going to show that one more time here. The square root of 25n squared is 5n. The square root of 100 is 10. So my two factors are 5n plus 10 and 5n minus 10. You can see how that's a lot faster than factoring by grouping if you recognize to do it. Again, if you don't, that's okay. If you know factoring by grouping, you get good at that, you can use that whenever you want. These two at the bottom are a little bit different. So here we have two different variables involved, but it works the same way. Actually, sorry, letter D does not. Letter C is, because those are both perfect squares. So I'm going to show that it actually works for this too, and later you are going to be doing stuff like this, where you have to factor stuff with two different variables. This is just one of the special cases. So we're going to do the square root of 16x squared, which is 4x, square root of 49y squared, which is 7y. And it's the same logic, even though now we have two variables, it's the exact same thing that we did up here. We're going to write that as 4x plus 7y and 4x minus 7y. Letter D is different because we have two variables that are multiplied by each other. Don't forget what we learned right before this. Factoring by a GCF is always your first step, and sometimes it simplifies it so that you don't need to factor at all. Anytime you have multiple variables multiplied by each other, if you have two variables in the same term, like an x and a y in that term, or the other x and y in that term, then look for a GCF as your first step. There we have our GCF of x, y. So we want to think about the most x's that we can factor out of here. We have two there. We only have one here. So the most x's that we can actually factor out is just the one. For y's, we have 1 there, we have 2 here. Most y's we can actually factor out is also just the 1. So I'm going to factor out x, y from both of these. That leaves me with x and minus 9y. That's as factored as it gets. When you have more than one variable, different variables, an x and a y or an m and an n, if you have different letters together, you're going to look for a GCF first. Sometimes it'll turn into something that you can factor more, but odds are it'll just end up like that. We can't really factor that expression anymore. That's the most we can do with it. Factoring is really one of the central themes in algebra. It's one of the most important ideas because we're finding solutions to this. Eventually, we'll be finding solutions. And solutions turn out to be really important, especially in parabolas. With everything that you've been dealing with so far, like linear functions, those are great at modeling really simple relationships. But when we get into things that have an exponent or even our exponential functions or an exponent higher than 2, they get more complicated than just the lines that you've been dealing with. These solutions are more valuable because they can actually, these expressions and equations are more valuable in general because you can describe more with it. They're more powerful than just a line on a graph. Factoring is one of the central skills that's tied to that. And it keeps coming up in Algebra 2 and Calculus. It's a central theme to all the math that you're going to be doing here, basically from now on. So really get good at it now. It takes a lot of practice to get good, especially at factoring by grouping, because it's got a lot of steps. But get good at it now so that you don't have to play catch up later.